capturing at this point, because vertices could fail, right? If you think of a network, a vertex might represent, say, a router, right? And an edge might represent a link. And in this particular problem, we are worrying about link failure, but not about the, say, the router failure, right? So let's just focusing on the link failure. By having k edge disjoint paths, what we are guaranteeing at that point is that at least k links have to fail before A and B will be disconnected, right? So that gives you, so if you think the probability of any link going down is P, then the probability of A and B getting disconnected is, right? So you have k edge disjoint paths. P to the power k, right? So P to the power k. So if P is relatively rare even, which is what you would expect, right? Links going down shouldn't be, something that happens every hour. So if the failure probability is small, then P to the power k is going to be quite small, right? So let's say you have a edge failure probability of 0.1%, okay? Just actually quite high, but let's say 0.1%, right? And then you have 3 edge disjoint paths, then your failure probability becomes 10 to the power minus 9, right? It should be pretty good for anybody. So now the question is whether we can, how do you, so you are given a network and you're asked, okay, how many edge disjoint paths are there between two vertices A and B? Okay, how would you solve that problem? Okay, you're given a network, you are given two vertices in the network A and B, and you are asked how many edge disjoint paths are there between A and B. How can we solve this problem? You could, but since we are trying to do this in the context of max flow, right? So there must be some connection to max flow, right? So that's why I'm asking this question. So let's look at this in the bipartite graph, right? So consider the paths from S to T that are part of a maximal matching. Okay? Are those paths edge disjoint or not? Yeah. Okay, so that tells you something, right? So then how do you solve this problem? Right. But bipartite, for you to find a bipartite matching, the graph has to be bipartite. But this is not a bipartite graph. I'm not saying you're, okay, obviously your answer is related to the solution, but not in the form that it is stated, because the graph I'm giving you is an arbitrary graph, it's not a bipartite graph. What else can you do? So the simple observation is that if you have two paths, right, that are not edge disjoint, then the combined capacity of these two paths is going to be constrained by the edge that they share. Correct? Okay, so now that, so can you tell me can you try to get to the next step from here? Which edge?
Because that has the maximum flow.
Right, but there is no flow, this is just a graph, right? It's just a regular graph. There is no, flows or capacities or whatever given to you, right? If you want to turn it into an instance of max flow, then you need to set the capacities as we did here, right? We said, okay, you're going to produce S and T and set the capacity of every edge to 1, and that's how we turn that into an instance of a max flow problem, right? So here is edge disjoint graph problem. The question is, how do you convert that into a max flow? Yes? What is K? Oh, no, gain. Let's just make it very clear, right? So I think you might have missed that, and maybe that's why you're having trouble. We just want to, given the graph, we just want to find out how many edge disjoint paths are there between A and B, right? We're not asking you to design a graph which has, the graph is given, you are not asked to modify the graph. All you're asked is, between A and B, how many edge disjoint paths are there?
Instead all that is dividing one and the sources, however many sources, max flow we get from the source to the sink, that will be the number of edge disjoint paths.
Right, more or less. But what is the source and what is the sink?
A is the source and B is the sink in that sense.
Okay, so if you that's fine. So you can set A to be the source and B to be the sink, and then you can ask for what is the maximum flow you can push through after setting all edge capacities to 1, and that should give you the number of edge disjoint paths. Okay, very good. So I will leave you with one other variation of the problem. Okay, so think of a business that manufactures and sells items. Okay, so this company has locations around the country, right? Okay, they both manufacture and sell. Okay, so they own the stores where they sell, and they also own the factories where they are producing. Okay, so they know think of them as cities, let's say, right? They have one location in each city, right? Just for simplifying the problem, think that they have one production facility and one store in each major city. Okay, so it may not be economical for them to produce everything that they can sell in a city in the same city itself, right? So, for instance, it might be economical to do all your production in Arkansas and have everything shipped to and sold in New York City, right? So maybe setting up a factory in New York City is not the easiest thing to do. So you have this company which can produce items in certain cities, sell items in different cities, okay? And now you want to find out, how do you transport items from places you produce to places where they are sold, right? And is it even possible given, let's say you may have capacity constraints, right? So you may not be able to, you may have only a limited ability to ship. Maybe you're running your own trucks, like you're not using a commercial shipping entity, so you have limited capacity to move goods from one location to another, right? So that's the overall problem. You have a graph, right? Each node in the graph can be either can either produce flow, right, or take out flow, because that corresponds to selling items, right? And for each node you are given this capacity to produce and also capacity to consume, right? And then you are also given edge capacities as in a max flow problem, because that represents how many trucks you have available to go between any two pair of cities and how you're going to use that, right? So now you're asked, okay, I have this, distribution of capacities and distribution of production and sales locations. Can you, tell me how much to transport on each of these, between each of these cities, so that I can, sell everything that I produce, right? Obviously, nobody wants to keep producing and accumulating in excess. Nor do they want to be in a situation where there is a demand, but they're not able to, have the product in the place, and therefore they're losing money, right? So they don't want either. So think of how this problem could be modeled in terms of match flow, okay? And we will revisit that some other time, okay? This time I will actually come back and ask you, and maybe it'll be the problem that you'll see in your next quiz, right? Okay, so now I'm going to move on to the next topic, which is going to be move on to another topic called amortized analysis. Okay. So the idea here is, instead of thinking about cost of individual operations, right, you consider the cost of the collection of operations, so that you can talk about the average cost across all of those operations. Okay. Why? Because there are often operations on data structures where a single operation may be quite expensive in the worst case, but for each operation that is expensive, there may be many other operations that are cheap. Okay, so by considering a collection of n operations, you might be able to come up with a more representative bound on the cost of each of those operations, instead of saying, okay, it can be on the worst case order of n, right? So instead, maybe we would give a cost that says, okay, n operations take only n log n time, right? Instead of saying a single operation might, in the worst case, take O of n time. Okay? So this term itself comes from finance, right? So in business, you buy an asset, and often the tax laws tell you you can't expense that cost in the first year. You have to depreciate that asset over its lifetime, and only count part of that depreciation as a business expense for tax purposes, okay? Or for the purposes of computing your profit, right? So how do you compute your profit? You take your revenue, subtract out your expenses, and the result is your profit, right? But how do you count the expense of a capital? If you set up a factory, well, the factory might cost enormous amount of money, right? So if you want to say what is your profit in the first year, it might be minus $100 million, right? So this is not good. So instead, if you think of the cost as the depreciation of capital, then that will be a much more reasonable figure compared to the revenue that you produce, and then you'll be able to give a profit estimate that's much more representative of your business's ability to generate profit in the future, right? As opposed to saying, oh, because I have this huge initial capital expense, I'm not able to, my profit is terrible. So the same thing that we are trying to do here. Okay, so let's. There are several techniques for doing amortized analysis. The first and the simplest one is the summation or aggregate method. That is, you, instead of considering the cost of any one operation, you just say, I'm going to consider a collection of n operations, and I'm going to talk about its overall cost. Okay, so let's look at some simple examples. Okay, so let T of n is, so you have n operations, you talk about the worst case running time for n of those operations. Okay, and then you just divide that by n to give the average cost per operation. Okay, so notice that this is somehow, this is not like saying, okay, I'll take the average complexity of my algorithm instead of taking the worst case complexity, right? So that's different, because it is possible that your worst case occurs again and again, right? Your amortized analysis done correctly will account for the possibility that your worst case occurs again and again, right? So in a sense that you're not saying that this is based on some optimistic assumptions. All you're saying is that given a collection of operations, okay, it may naturally be the case that some operations take more time and other operations take less time, right? So by combining the cost of all of those operations together, I'm able to sort of come up with something more representative of how long it takes to do an operation on the average. And in particular, even though you're saying T of n by n, right? So when you repeat this n times, you do get the worst case runtime of all of those n operations. So let's look at this example, right? So this is a binary counter, right? So the binary counter is kept in a bit array, right? B. Okay, so B has, let's say n bits, 0 through n. Okay, the way you increment it is that, so how does bit incrementing works, right? So what you're going to do is that if you're going to go from the right end of the binary number, right, and look for the first 0, right, then you turn that into 1. Okay, that's increment, right? Because if it is 0, all 0, then you're going to take the least significant bit and turn it into 1. So it becomes 0, becomes 1, right? Let's say you have, your number is 1. Now the least significant 0 bit is in the 2's position, right? So in that case, what you're going to do is, did I say something? I think I said something wrong, right? So, okay, anyways, so let's go through this algorithm, which is obviously easy enough to understand, right? So if I equal to 0, if the 0th bit is 0, then you're going to come out of the loop and you're going to set that b of 0 equal to 1, right? Let's say you have a number 1, then b of 0 will be 1, so you go into the loop, right? So you turn that into 0, and then you do I plus plus. Now you are at I equal to 1. Now you try b of 1, right? So it is 0 now, because we are talking about number 1, which only has b of 0 as 1. So therefore, the loop is no longer applicable, so you come out and do it. Right? So basically what it says is that you basically are going to
make all 1 0.
right. So you have a number where there are k bits, all of them are 1, right? And then you have a 0, and then you have n minus k minus 1 bits, right? So this, you can think of any value of a number, right? There are some k bits, all of which, the least significant k bits, all of which are 1, then there is a 0, and then the remaining is whatever, right? So in this case, what you are going to do is, you're going to turn all of these 1s into 0, and then turn this into a 1, right? So that means if k equal to 0, right, then you're just turning something. So let's say that all of these, let's say all of these are 0, right? Just for simplicity, it doesn't have to be. All of these are 0, let's say for simplicity. Now, if your original number is 0, then k will be 0, right? So the very first bit you set to 1 and move on. if your number was 1, then k will be equal to 1, right? So then what you're going to do is you're going to set the least significant bit to 0 and the second least significant bit to 1. So you get number 2, right? And so on. Okay, so the fact that it does binary increment, I guess, is not that important or interesting. The question really is, how do you account for the cost of this operation? Because you can see that the worst case, if you consider any single increment, the worst case is n, right? Because you may have to traverse through all of the bits, because everything except the leading bit might be 1. So you have to traverse the entire array, so the worst case cost of incrementing could be O of n, right? But then that seems high, right? Because you do have this ability that I can stop as soon as you. Okay, so now can you guess? So I guess all of you know that its cost is going to be less than n, right? So if you consider 2 to the power n operations, right? Which means that you're going through an entire cycle of increment, right? So until the whole counter wraps around. Okay? So if you consider 2 to the power n operations, okay, the worst case analysis gives you that each of these 2 to the power n operations could take O of n time, right? What do you think is more realistic? Right? What is the amortized cost? What can you can obviously see that the worst case doesn't occur all the time, right? So if you consider a sequence of 2 to the power n increments, it's certainly less than n times 2 to the power n, right? This is clear. But can you guess what would be the number? Is the average cost n by 2? What do you think is the average cost? So to help with this, think how often you will not execute this loop even once. How often, right, out of these 2 to the power n operations, what fraction of those operations will not execute this loop? No. There are 2 to the power n operations, right? Out of the 2 to the power n operations, what fraction of them won't execute this loop at all, right? Because they won't execute this loop at all because of what? When, which bit? Right. That is 0. So how often is that going to be? Half the time, right? So that tells you something, right? Half the time you're done with one operation, right? So how many times will you go through this once? 1/4 of the time, right? So you can see that there is going to be some kind of a geometric progression, right? So you're going to spend, you're going to finish in 1 unit of time half the time, and 2 units of time in 1/4 of the time, and so on, right? So so this is the formula, right? So m to the power 1 by 2 to the power I, right? So n equal to 1, then you will do half the time you will do, and so if you calculate that, it just comes out to be 2. Okay, and then you can see that 1 plus half plus, right? That goes to 2, right? So this is pretty clear that. Okay. So clearly, the example shows you that if you do the amortized analysis, you get a much more representative and much smaller number than the worst case. Okay? And then again, I want to say this a million times, right? We are not talking about average case, right? We are not saying assume that input is distributed in a certain way and therefore I expect the average case and therefore no. We are just saying that instead of thinking about a single operation, think about the combined cost of many operations, right? And for those operations, what is the total cost? Okay, so there are other ways to do this, which can be even simpler. Instead of talking about the summation, there are simpler ways to think about the problem, and one of them is called charging method, right? So the idea is that you are going to associate higher costs with certain operations. Okay, so the operation itself may seem to take only 1 unit of time, but you will assign it 2 units of time, so that you can use this, extra cost to pay for something else down the line. Okay, so for instance, we could say that we charge 2 units to change a 0 to 1. Okay, even though the operation of changing a 0 to 1 should cost only 1 unit, but we are willing to say 2 units. Okay, so why? Because we are going to say you'll never charge for changing a 1 to 0. Okay, because we already charged twice for going from 0 to 1. That 2 should be able to also pay for changing it back from 1 to 0. Right? Okay, so now when you use the charging method, you need to make sure that you have charged enough, right? So you need to really make sure that for this to work correct, for this to be correct, it should be the case that you can change a 1 to 0 only once, right? If somehow you could change a 1 to 0 3 times, then this should become 4, right? So but in this case, we know that it can change from 0 to 1. Once it has changed from 0 to 1, it can only change once from 1 back to 0. So we're going to charge. So it's enough to charge 2 units. And now the analysis becomes, so trivial, right? Because again, remember, we are only going to charge for changing a 0 to 1. Okay? And you can see that this loop changes 1s to 0s, right? So you can ignore the cost of this loop because you're not going to charge for changing any 1 to 0. You're only going to charge for changing 0 to 1, right? Which means that you only have to consider line 1 and this line, right? So which means that you basically throw out the loop and you analyze and you say, okay, it's going to cost 1 unit per increment. Right? So again, it's not that the answer is different, it is just that the reasoning involved to arrive at the answer is much simpler by thinking about it in terms of charging instead of doing the summation. Right? The summation is a bit more, requires a bit more work, whereas the charging method is, the argument is much simpler and easier to see. So consider a stack, right? Stack has push and pop k, okay, which can pop k elements on the top of the stack, right? But push, obviously pushes only one element because you have to say what element to push, right? So again, if you think about the worst case, let's say you do a mix of n pushes and pop, right? Notice that the worst case cost of a pop is O of n, right? Because you might pop the entire stack, right? So again, the worst case of any single operation is quite high. So what we would like to know, consider the n operations together and say, okay, what is the overall cost? So one way to do this, again using this charging method, is we charge 2 units for each push. Okay, now pops don't have to pay anything because you already charged 2 for each push, and any element pushed can be popped only once, right? So the cost of pop can be paid for from the extra unit that you charge to push. So now you can do your analysis ignoring pops, right? And obviously there are only n operations, and out of n operations, there could be just n pushes at most, right? Or there could be, k pops and n minus k pushes. Well, that will cost less than n pushes because pops cost nothing in our model, right? So that means you're going to, if you have 10 n operations, it's going to cost 2n, right? So again, using the charging method, it's very easy to understand how you can arrive at a lower cost per operation. So, the charging method is simple, but it has some limits because you have to, essentially combine operations together, right? So we're saying push, I'm going to pay for the pops from push, right? But if you have a situation where the potential method is a little bit more general, because instead of just looking at the operations, it also allows you to look at the data structure that remains after you do the operations. Okay? So you can store some charges that you have previously charged into the data structure, and then when the data structure is modified subsequently using some operation, the cost of those operations can be paid for from the data structure itself. Right? So it's basically like saying, okay, without having a place to pool together the credits, I need to associate charges and so basically in the charging method, I have to pick operation A and operation B and then pair them up, right? I have no place to sort of pool together the cost. The potential method gives me a way to pool together the cost so that I can do a more complex analysis. And the way to think about it is like in physics, you have a potential energy. The data structure, you can associate the data structure with some potential energy, and as the data structure changes, the changes to the data structure may increase its potential energy, in which case you have to, pay for those, or the change may decrease its potential energy, which means that the difference in the potential energy is available to pay for the current operation. So let's look at the stack example again, right? Each push costs 2 units, and in this case, we are going to associate the cost with the potential of the data structure. So we are going to say, yes, a stack with k elements has a potential energy of 2k. Okay? And so whenever you pop I elements, right? So let's say you start with let's say the stack has, let's say the stack has m elements, okay? And so the potential energy equals 2m, right? Now you do pop.
So what will be minus m?
What?
Won't it be like minus m? Because initially it is empty, we can say that it has 0 potential energy, and then
You can't pop then, right?
plus m, and then we go back to 0.
Right.
Go on.
Right. So initially the stack has 0 potential energy. Okay. So when you push, its potential energy increases. Right. So let's consider the case you have L, right, which means potential energy equals 2L. Now if you do push, then you have L plus 1, right? Which means that potential energy equals 2L plus 2, which means that charge equal to 2, right? Because the potential energy has increased by 2 units. Therefore, that increase has to be paid for, right? So the cost of the push operation is going to be 2. Okay. Now, if you look at the pop operation, you're going to pop k elements. So the potential energy after the pop is 2 into m minus k, right? Which means that I'm sorry, so it's not 2k, it should be just okay. The potential energy of a stack with m elements should be just m. Okay. So now, so let's say you start with a stack of size L. The potential energy is L. You push. Now your stack length becomes L plus 1. That means the potential energy changes to L plus 1. Now you have to pay for, you know, 1 is the cost of push, and 1 is the increase in potential energy. Right? So you need to still account for the cost of the operation. So what you're going to do is you're going to say, when I push, I'm going to take 1 unit off for the cost of the operation itself, and then I need 1 more unit because the potential energy of the data center. Okay. So now when you pop, the potential energy is decreased from m to m minus k, which means that k units of potential energy has been released, which can now pay for the cost of the pop. So again, there's no the answer itself is not different, but thinking about it in terms of potential and so on allows you to get to the answer in a simpler way. So now let's
So we have cost for the structure, for the data structure.
Correct.
And cost for the operation.
Correct.
As well?
Right.
So here.
So the essentially the data structure cost, that is just a way to sort of store and keep track of the costs you have paid for in the past, right? Data structure is just a convenient place to store the excess in charges that you have paid. So for instance, you're going to pay 2 units for the cost of push. Now only 1 is needed for push itself. So you need to remember that I have an excess of 1, and you remember it by storing it by thinking of it as a potential energy associated with the data structure.
And the pop here will have no cost.
So the pop obviously needs k units of time, all of which can be paid before by the difference in potential energy. Right? Okay, so so now let's look at something more real, right? So hash tables, right? So so one of the issues with hash tables is that they have you expect to have constant time access, but if there are many collisions, then you also know that you have a very bad worst case behavior, which is could be O of n. And the most important factor in this is how full your table is, right? So if you have n elements, right, in a hash table, then if the number of elements in the hash table gets close to the size of the hash table, then you're going to have many collisions, and your performance will become poor, right? So what you want to do is instead, whenever so you can of course figure out what is the right size of a hash table for your problem, right? and then make sure that there are enough, the hash table is large enough that collisions won't occur frequently, right? Now, how many of you think that's feasible to estimate what should be the hash table size? So nobody's going to risk giving an answer.
It could be wasteful if it is not.
So obviously, right, you're right. So you don't want to make it too big because, well, obviously that's the whole purpose of using hash table as opposed to, let's say, directly indexed array is so that you limit the space that is needed, right? So, but if the size is too small, then there will be too many collisions, and you will very quickly get to the worst case behavior instead of expected O of 1 lookup time. So, so one way to deal with the problem is to say, well, I can't figure out exactly how big the table needs to be. So what I'm going to do is I'm going to resize the table as if it grows, or maybe even if it shrinks. For now, let's just focus on the simpler case where the table can only grow, right? You can only insert. Let's say you can never delete. Okay, there are a lot of applications where this happens, right? You don't have to delete, you just have to insert. Okay, so in that case, as the table grows, you're going to increase the size of the table. Okay, but unfortunately, increase the size of the hash table means essentially rebuilding hash table, right? So let's say there are 100 elements in the hash table and you want to resize it, then you basically have to remove all these 100 elements, create a new hash table and insert all these 100 elements plus the new element, 101st element that you want to insert, right? So just this one operation, one insert operation takes enormous amount of time as compared to, let's say, any other normal insert. So if you say, well, again, if I have a table of size n, this says that in some cases the cost of my insertion is n, right, which is a disaster. So the question is whether we can come up with something better. Okay, so obviously you can try to guess right, and then you can resize. So this is never possible, right? I would say there is a negligible probability that you will be able to guess the right size for a table, right? Because so what you would like is an algorithm that allows you to deal with whatever size, right? So and you'll rehash as needed, but then you don't want to blindly rehash, because if you do, then the operations can become quite expensive. So one thing you can do is you can amortize the cost and then do an amortized analysis that hopefully will tell you that it doesn't cost too much. So how do we do this? So let's amortize the cost of rehashing over other hash table operations, right? Because rehashing doesn't have to happen often. So let's say we rehash after a large number of operations. Okay, so it doesn't matter how large this number is, right? So let's say for argument's sake that it is 1,000. Okay, so now the first 1,000 operations, right? You are going to insert 1,000 times. Let's for the moment, forget about lookups. Okay, just for simplicity of analysis. Okay, so you're going to have 1,000 inserts, but then after 1,000 inserts, you have to pay for the rehash, right? And rehash requires essentially reinserting all of those elements. So you're going to need 1,000 units for the initial insertion and 1,000 units for the rehash. Okay, so 2,000. That doesn't look bad, right? Okay, looks like we are paying twice. Okay. So amortized cost seems like 2. So now let's see what happens when we hit 2,000, right? So when we get to 2,000, we have, the first rehash, up to the first rehash, we spent
1,000, 2,000.
2000, right? So when we finished inserting 1000 elements, we have paid already 2000. Now we insert the next 1000, so we pay 1000 for that. And now we have to rehash again because now we are done with 2000 operations. So now we have 2000 elements to rehash. So that costs 2K. Now you see that has cost 5K, right? So 2K elements, its cost is 5K. Well, it's not as good as last time, now 2.5 per operation. So let's see what happens when you go to 3000. Well, once again,
This is for all insertions, I think.
yeah,
And then
the
this-
total cost so far, okay? So you have 3K insertions so far, okay? The rehash you performed at 1000 required 1K. The rehash you performed at 2000 required 2K operations. The rehash you perform at 3000 requires 3K. So that becomes 9K. And if you look at this form of this, right, this has 1 plus 2 plus 3. So this is an n square type of thing, right? So this grows like n square, and since you want to find the cost per operation, that n square will get divided by n. But still, you can see that the average cost per operation is increasing linearly with n. Okay? So if you keep, rehashing after some number of insertions, then as the table grows larger and larger, you will end up spending, O of n time per insertion, right, as opposed to O of 1 time. Okay. So what can we do? How can we make this better? Does it mean that we shouldn't rehash, or is there some way to rehash so that the cost won't increase this way? So am I correctly inferring that you have not heard about hashtag table resizes in the past? Or should I conclude that you heard about it but possibly forgotten?
I think there's doubling and like
Okay,
Well-
so what happens when you double?
it will not be like every 1K, like it will be 1K, 2K, 4K.
Okay, so you remember part of the solution, so but what does that mean in terms of the cost? Is that any better, for instance? Okay. So let's double the hash table each time it gets full. Okay? So now, what is the cost? Okay? So the first time you hash, it's kind of similar thing, right? So you do n inserts, and then you reach your limit, and you're going to rehash. Okay? This n could be 1K, whatever, doesn't really matter. Okay? So now, when you reach 2n, the hash table size reaches 2n, you're going to rehash again, right? So that requires the cost of P of n, right? Because that's what, in order to reach n, you got there, and then you are going to do n more insertions, and then now you have to do 2n rehashes, because at this point, you have 2n elements in the table, all of them have to be rehashed, so you have 2n, right? So again, no difference so far, right? So we still have 5n. But when you get to 4n, right, so it goes to 11n. So somehow, is it any better? So if you sit down and write down the recurrence, you will say that you have the recurrence T of n equals T of n by 2 plus 1.5n. Okay? You can derive this in your spare time, but you can easily verify that each of these cases that formula works. Okay, and so you have T of n equal T of n by 2 plus 1.5n. You can apply your master theorem and it will tell you that it
It feels
is
kind
linear.
of like a reverse engineering in the sense that we are trying to count the cost that it takes to rehash,
Mhm.
and we are increasing our problem size to match the cost of the rehash.
Right, so algorithm design, right, when you start from, often you want to design an algorithm with a certain complexity, right? So that is somewhat of a reverse engineering process, right? Because given the complexity, how do you figure out, how do you design an algorithm to get that complexity? So now we can do this in a simpler, we can do a simpler analysis, right? So what we will do is that we can think of it in terms of charging. So what you're going to do is each insert operation is going to be charged 3 units. Okay? Why? So the reason why I have to charge 3 is because remember that the element that you inserted, very first element you inserted into the hash table has to be rehashed many, many times, right? It's not any element that you inserted in the last run, you're going to just rehash once. But any element you inserted in the first run is going to be rehashed many times, right? So it's not enough to just charge 2 units because an element is actually being rehashed more than once. So we are going to charge 3 units, and the way we are going to do this is you're going to insert an element, right? So that you're going to use, that's going to cost 1 unit. At the end of the current run, the element that you inserted, right, has to be rehashed. So you're going to pay 1 more unit for that. Now when you started this run, there are already some elements. You need to rehash them too at the end. But notice that this run will last as long as the initial number of elements in the table, right? Because our runs are of the size, like 1,000, 2,000, 4,000, 8,000, and so on, right? So when you go from, let's say, 4,000 to 8,000, you start with 4,000 elements in the table, and you're going to go to 8,000. That means you're going to insert 4,000 new elements in the place of the original 4,000, which means that each insertion, if you make it pay once for an existing element, then rehashing of an existing element can also be accounted. So now you're going to pay 3 units, 1 for the insert, 1 for rehashing that element itself, and 1 for rehashing an element that was already present at the beginning of the run. And now we are done, right? So now that with this simple charging, 3 units per insert, you're paid for all rehashing operations, right? So now it tells you that with the 3m cost, you're going to be able to, so you can rehash as you want. That increases the cost of your inserts by a factor of 3, right? Which may not be, you might think that's significant, and yes, it's not 1.2 times more, it is 3 times more. But then you have to also take into account that in this analysis, we kind of ignored finds, right? Lookups were ignored. Most of the time when you use a hash table, lookups are more than inserts, right? So if you consider the combined cost of lookups and inserts, then your factor doesn't have to be 3, right? It's going to be smaller than that because lookups are going to be 1 unit, right? So they are not being charged anything. So if, let's say, you have 2 lookups for each insert, right? Then the total cost is 3n, right? And the total number of operations is also only 3n, right? Because you have n inserts, 2n lookups. So that's 3n operations. And each insert costs 3 units, which means n inserts cost 3n. So if you have this relatively reasonable model of how many lookups versus how many inserts, you end up getting, your costs are not 3 times, they almost become the same, almost the same. Okay, So I made a mistake in my calculation, which was, it should have been, I guess, 5 by 3, right? So it should have been, because the 2n lookup still costs 2n time, and the n inserts cost 3n, so the total cost is 5n, but then 5n is divided by 3n operations, which gives you a cost of 5 by 3, which is more acceptable than, let's say, 3 times the cost when you don't resize. You can also use, the potential method, and you can say that when you typically write, so the way hash tables are resized is you think about how many elements are there in the table, and you express what is called a load factor, right? So you say, okay, the hash table has 100 cells, and I have 700 elements. That means the load factor is 700 by 1000.7, right? So you typically keep the load factor between 0.5 and 1. Okay, and so generally, and the reason is that if, let's say you resize when the load factor is 1. Now you're going to double the size. Therefore, immediately after doubling the size, your load factor is going to drop from 1 to 0.5. Right? So the load factor will generally stay between x and x by 2. Right? X and 0.5x. Let's say in this case 0.5 and 1. Then you can define the potential as 0 when it is less than or equal to 0.5. Again, if you don't think about deletes, then the table should never go below 0.5. No, table can be below 0.5 when you start. But then you say that those at that point it doesn't store any energy. So the way is that as pressure builds in terms of space pressure, then that's what it's like compressing a spring, right? There's a pressure, you're compressing a spring. That's how the energy comes out, right? And you define some function like this, and then you can work through the same types of calculations and realize that, okay, so it still gives you. So now I want to ask you a few questions, which you can either think about it, and we'll discuss the next time. So in particular, if you have a factor other than 2, let's say I increase by a factor of 1.2, right? Each time I resize, I increase it only by 1.2. Then what is my amortized cost? Is it constant, or is it is it linear or log n? Does it become? Our goal is constant, right? Amortized cost of constant, and we know that if we double the capacity each time we hit the limit, we get constant time, right? What happens if you increase it not doubling it, but increasing it by a factor of 1.2? What do you think is going to happen? You should have a quick guess, right? You have enough experience to say, to come up with a guess. It may be wrong. How does it matter, right? See, again, this is about a geometric progression, right? So we saw a geometric progression, right? Once you have a geometric progression, it's going to sum up to a constant no matter what the factor is, as long as the factor is, it must be a decreasing geometric progression, of course, right? So as long as that is the case, you will have a constant time. So it doesn't matter. But obviously, the constant will increase. Right? For 2, the constant was, like 3 or something like that. For 1.2, the constant will be much higher. Right? So that's all. So the other question is, what happens when you have both insertions and deletions? Can you come up with an amortized analysis in the presence of both insertion and deletion? Okay? So that's a problem for you to work out, right? So if you, I want you to think about it, and we will discuss it in class next time. And if you are not telling me enough about, if you haven't done the work, then you can, I can surely ask that question in the exam, right? So it's one of those. Okay, so now let's talk about related data structure. So we know that when you have linked lists are very common, right? So when you don't know the number of elements that you might have, yeah, the linked list is a useful data structure, right? But as I said before, on modern processors, linked lists are very inefficient. Okay? So vectors are arrays basically, right? Except that these are arrays that are dynamically resized. Okay? So they give you sort of, so if you look at any class library, they will typically have very similar operations for linked lists and vectors, right? You can insert elements, you can you can get to the ith element and so on. But since vectors are implemented using arrays, random access is efficient. Okay? But let's not worry about random access because we are talking about taking an application that uses linked lists and seeing whether it works fine with vectors. Okay? And but in order to see vectors as arrays have fixed capacity, you need to dynamically resize it, which means that you have to allocate a new array and copy the original content of the array to the new location. Right? So this is how vectors have to be implemented. So this is kind of similar to hash tables, right? Because hash table you start with a certain size. Once it gets full, you rehash it and you reallocate it in a different place. So you can do the same thing with vectors, right? And when you do that, again, if you do an amortized analysis, you can show that the cost of, even with the dynamic resizing, the amortized cost of insertion in a vector, right, is constant. Okay, similar to the way you prove it for hash tables, you can prove that also for vectors. And strings are an example of, a common example, right? I mean, you often use we'll use string data type, and internally any self-respecting language or class library will implement strings using some kind of a vector, and strings will be resized as you perform operations like concatenating two strings, right? So obviously, if you're working with C, then C doesn't have self-respecting data structures, right? So then you don't get any of this. Okay, so I'm not going to. We'll stop here. So the last topic here is disjoint sets, which we will look at different ways of implementing disjoint sets and talk about the amortized cost of this implementation. You might recall that disjoint sets is what we used in the example in the Kruskal algorithm, right? So it's a very, very useful data structure and a very nice and interesting data structure because it allows, again, in the Kruskal algorithm, right? So you're asked this question: are these in two distinct components of the graph, or are they already connected together? And this seems like a somewhat complicated question to answer, but in fact, using disjoint set data structure, you can answer it very, very efficiently. Okay, so we'll come back to that on Thursday. So I presume all of you have seen, how you did in your exam. You can come and see me during my office hours to look at your exam papers. For those of you who scored below the average, I want you to make an appointment to see me. Okay, and obviously I would prefer to see you during my office hours, but if you have a conflict at that time, then let me know that there is a conflict, and tell me what other time is going to work for you. Okay.